Muito bem, mais uma vez boa tarde. Essa é a terceira aula agora do curso número 2, ministrado pelo professor Bernd Hofmann. Please, Professor Hofmann.
Thank you. I'm happy that so many people are still here, even if the time is late. Many of you heard my first lecture last week, and I will continue in some sense now. In my first talk, I presented you a series of applications, 1 linear, 3 nonlinear, and I said that my setting is 1 for linear inverse problems, 1 for nonlinear inverse problems. I recall I had 1 star for the linear problems. A is a linear forward operator, and X is the solution to be reconstructed. And yeah, we have nice definition for well-posedness, ill-posedness. Range of A closed, then well-posed, range of A not closed, then ill-posed. And so the world is rather clear. My second was 2 stars, and today all my slides will be in this setting. In both cases, I assume that we have noisy data, Y delta, with a deterministic noise model, norm of Y minus Y delta norms smaller than delta. Delta is the noise level, all well known in the scenery. Because I mostly will have on my slides only the 2-star version, maybe you remember local ill-posedness, local well-posedness I introduced the last time. Some words about the linear. In 2000, around 2000, I really believed that the regularization theory for the star problems, for the linear problems, is gone, is over. All is fine. Nothing will happen. It does not make sense to think about, and so. Then, in 2003, there were a couple of papers by Peter Mattei from VIAS in Berlin and Bernd from the Radon Institute in Linz, and they used so-called index functions, which are nothing but, I will have it also in the slides, which is nothing but functions which characterize also rates. Let's say you have here some delta level, and you have here an index function. This index function, before I never heard this, comes from the theory of variable Hilbert scales, and were introduced in the 1990s by Markus Hägland. He works in Canberra in Australia. He's from Swiss, and he had no job in Europe. And then he went for 1 year to Australia, and he is still there. It's a couple of years. So, and this is a very interesting theory, variable Hilbert scales. But for me, it was only interesting, okay, such rate functions you can characterize as index function. What does it mean? It means this is a function, this is the 0, it comes from 0, is, let's say, strictly growing, and characterizes a behavior of an error. And so for me, this idea of index function, of working with index function, was so interesting that I said, okay, there is still much space in linear regularization theory to do so. And so in my talk today, mostly in the context of the nonlinear problems, you will find many index functions there, because they play a very important role. What is the, what are the most important? One kind is the index functions of the following type: power type, phi of t is anything like c multiplied by t of nu, and yeah, the nu is greater than 0 and smaller than infinity anyway. And as you see, in this scenario, you have concave and convex functions there. But in principle, for our problems, for our regularization theory, mostly only the convex type is of interest. Convex type is the interesting type. And yeah, so in principle, you must reduce the things up to 1 here. And if you have an error estimate which is proportional to delta, let's say I will write it here in delta, it seems to be better for understanding of the things. If the exponent is 1, then you are in a well-known case of well-posed problems, and all better results are curious or suspicious anyway. And so in principle, these convex index functions play an important role for me. And you will find many of this type. Another type is the type of logarithmic functions which occurs here. And so if you have this exponent mu smaller and smaller, then it's clear the function will have a behavior more and more in such a way. Yeah, and the engineers are very enthusiastic. If I say the most or the best possible situation we have here in regularization theory should be the nu a half error in the form big O of square root of delta. Then they do not smile very much, because they say, okay, if I buy a new measuring tool which is 100 times better, the result is only 10 times better. That's not nice. But often one cannot achieve this nice rate. One can only achieve a logarithmic rate. Logarithmic type, I hope I have a... And so this phi of delta is 1 over, for example, logarithmic of 1 over delta to some exponent again in this way. And it's clear you will find here still more such. And in the simplest way, yeah, if I say if such problems occur, for example, in inverse heat conduction problem often, if the smoothness is appropriate there, as I say to the engineers, okay, you must buy a measuring tool which is 10 to the power 6 better, and then really I can ensure up to some constant that your result will be 6 times better. Then they also very unhappily because, but this is the realistic situation. There are some guys in our community, for example, Andreas Neubauer in Linz. He says, only these 2 types I do accept. Other things do not exist for me. Okay, this is one standpoint, but from my point of view, there is something in between and something else. For example, if this yellow one is too good for our situation, yeah, there may happen anything else. For example, instead of the log, you can make a log-log, or log-log-log, or log-log-log-log, and so on. And so, and in this time after 2003, with the Peter Mattei and Sergei Bereversev's paper, many people considered such things, wanted to try it, and they used it. And said, okay, I use for my theory, I stay at the moment at the linear, I say, okay, my solution is phi of A star A with some source element, and this is a well-known source condition, and phi is concave index function. you find in this time after 2003 couple of papers, maybe more than 10, which work with this and say, okay, we have results, and assuming that the solution has this source condition with any such phi, then we have nice results. So I discussed with Peter Mattei when he was in Chemnitz in 2005 or so, is this an assumption? What does it mean? So we must solve this. And Peter is a very good guy from analysis. He comes from the Jena school, retrieval and all these names, and he said, okay, we have to discuss it. And really, we could make a paper, 4 pages, to show for every element. Now we are clearly in the Hilbert space. In the Hilbert space, for every element x dagger, there is one concave index function phi together with some source element w such that such a source condition exists. So it's not an assumption. It really exists. So you can, for every element, assume such a source condition. And if, for example, your logarithmic source if the source condition is so unflat, then in principle the solution is unsmooth, very unsmooth. If you have this solution is too unsmooth to satisfy such a logarithmic 10 to the 6 and 6 times better source condition, then you try it with log-log, and you try it with log-log-log, and so on. But you always have it. You always find it. So in principle, for the analysis, not for the practitioner, it's not so really good. But for the theory, it's nice. For the theory, it's very nice, and you can have it. So with this little paper, we could make clear some point, and in the time after, it was not an assumption. It was a realistic situation, and from time to time you can verify this also. Before I start, another point. On the blackboard I stay on the 1-star version because you will find it in the 2-star version then again, but it is better to explain this in the 1-star version. Now we assume that such a form of phi. For example, I make it with an example. Let's say x dagger is a star, let's say V. This is a very well-known form of source condition. I think Charles Scratch in this book in '84, he showed you get such a square root of delta rate here. And now we like it to have this. But my solution does not. The solution is too unsmooth. What will we do? What shall we do there? So my idea was at this point, okay, if this is I tell it benchmark source condition, it would be fine. We'd like to have it. But the world is bad, and we haven't it. So let's do the second point as follows. Let's measure. I assume that A is injective here, and otherwise it's a technical problem. You must handle it in null space, and it's only of technical meaning, but I assume this. I say, let's define such a distance function with focus on this element. And this distance function should depend on some radius. And we say, what is the infimum of such norms between this x dagger and some A star V's here in this form? Overall V's. So if you have injective still in Hilbert space, you know the range of A orthogonal to the the null space of A orthogonal to the range of A star gives the whole space. So if you take this infimum, then this R is still hidden here in this at this point. You get 0 for this infimum. So it makes no sense to consider this. But now this was the main idea. I think it's, I'm a little bit proud on this, that my group could discuss this in the first round. Yeah, what happens, however, if you do not take all, but you only take all source elements which are in a ball with radius r? So, and it's clear in such case you get a well-defined number here, in general positive number, and this distance function for a fixed x star is a function with following properties. Here's r equals 0, r goes to infinity, and you start here, and it's a decreasing function tending to 0 and has a decay, has a strictly decay, is convex, one can show this, and so in principle, this function, the character of this function, expresses the degree of violation of my element x dagger with respect to my benchmark source condition. This is the idea. So in principle, this distance function characterizes the element x dagger with respect to the source condition, the benchmark source condition. Exactly, it's an equivalent form of a characterization. You can do it in another form, but it characterizes it. So in principle, if this is exactly satisfied, you have some v with some fixed radius, and then this goes down and comes to the 0. Anyway, this is the case, benchmark source condition satisfied, then it lands here and, of course, stays 0. But if this benchmark source condition is violated, you do not have a 0, but you have a decay to 0 here. So this distance function, if you have it, is helpful for characterizing in the same manner the characteristics of x dagger. It is characterized, we know there is a phi and so on, but this benchmark source condition we prescribe and say, okay, it will not be satisfied, but we have such a distance function. We know or can evaluate this distance function and can have so it's clear, if this distance function goes to 0 very fast, then the violation is small. If it goes very slow in a logarithmic way, then the violation is very hard. It's far away from the benchmark source condition. And really, we will have it also in the slides then. This distance function can be characterized for computing, for evaluating rates, convergence rates for regularization methods. It depends on this. And what is this R? Why this R is not why in regularization we do not need it. But this R is free. You can use it, and you can evaluate it with other terms, and this evaluation gives then really the rate. So this is a very helpful tool, and we started here in the linear way and got some results. These are two very important tools for having this in the linear way. For nonlinear problems, really you can substitute this A by, for example, the Frechet derivative or Gateau derivative or Gateau-like derivative at this point, and can handle the technical things in the same manner. So this, please excuse my long introduction, but I think it's better to explain this in the linear case. In the second part, I will, in my third lecture for Thursday is not so long, so I will stop today after this point, so I will skip then and continue on Thursday, so please do not be so angry to see this. this list here. There are a couple of colleagues who do regularization theory. I wrote a book with Thomas Schuster from Saarbrücken, and he told me, I believe that I do regularization theory in Banach spaces without knowing all about Hilbert spaces. This is not my opinion. I believe if I have to do something regularization theory in Banach spaces, I must know all about Hilbert spaces, and I try to adapt something there, nothing but this. So yeah, we nevertheless the book was successfully book published, and yeah, so this is only a philosophy problem. Therefore, point 2, learning from Hilbert spaces. And I will show you a couple of results in Hilbert spaces, and I will come back to one point I had in my first lecture, autoconvolution problem. This autoconvolution problem, I will take it here in the simpler form in Hilbert spaces. I will show you that all bad things which can happen there. So, and therefore it's a quadratic problem. Everybody says, okay, nonlinear problems, which are very complicated, internal structure, but here this internal structure is so simple, and nevertheless, the situation is very bad. So I like simple examples very much. So, so one can see it's like, yeah, like X-ray. You see it very, very good. Insert, I really do Banach spaces, and I give a third characterization of such, this is nothing but the smoothness of the solution, the so-called variational source conditions or variational inequalities in order to get convergence rate in regularization. It's a rather modern form of characterizing the smoothness. In addition to these two, and I was rather happy that I was included in a project with Ottmar Scherzer, Barbara Kaltenbacher in 2007, and we could start with these points, and I was not sure that so many people will put on these things, and now I think this is really one of the best ways to characterizing smoothness. One word before we go on here on smoothness. Already in the lecture of Professor Baumeister in the last week, it was mentioned that Schock in the 1980s showed that you cannot have convergence rates in regularization if you do not have smoothness. So no rate exists for all elements in the Hilbert space. So Banach spaces, of course, the situation is the same. Yeah, so it is clear you need smoothness assumption, you need restrictions of the solution, for, in general in such a form like source condition, in such a form like distance function, decay rates, or in form of such variational source conditions. My view in this point is, what is smoothness in my sense? Smoothness denotes is the character of the solution, let's say the solution smoothness, if this is a smoothness. Now, and this is important, this is not always clear in many papers. Smoothness not intrinsic for its element if you look at X dagger, but smoothness with respect to the forward operator, or in the nonlinear case, with respect to some linearization of the forward operator. So that means both must fit the solution character and the operator character. And only if they fit, then you get convergence rates. And this is my my philosophy there, and I'm rather sure that one must understand this, otherwise one cannot interpret such things in this way. Some words here about this. Variational source conditions or variation inequalities which form these source conditions they are a rather strange thing. If you have it seen it first time, you say, bah, a mathematician has formulated a formula. Nobody knows what does it mean. It looks rather strange. So in this chapter, some words about, when do they exist, when do they occur, and they occur at many points. And real nice fact. Since about, let's say, 4 months, I know when reading the habilitation thesis of Jens Fleming in my department, that there is an analog to our theorem with Peter Mattei of the existence of such phi and w for the Banach space regularization theory and variational source condition. Jens showed that under very simple assumptions, for example, if the nonlinear problem has a unique solution in a small domain around her, there exist always such variation source conditions. They really exist. They can be assumed. It is not a hard assumption. They do exist in any case. And so we have an analog to the Hilbert space situation also in the Banach space. You will see it then a little bit more. I think maybe on Thursday, I'll see if we have not so much time. We were extremely proud that one argument could be, we could fight against this argument. Say that, okay, you make nice things. You make such distance function. You make such source condition in generalized form. But in principle, it's the same as all do, but in another written form. But now we really come to Banach space. In L1 regularization, and we are in a Banach space which is non-reflexive. In L1 regularization, you have a situation, I will show it, you have a situation where no really source condition exists and no approximate source condition exists. But variational source conditions can be shown. So this is, we are very happy about, because this argument comes always again and again. You can do more than with a traditional argument. So this should be the content of the 5th point. And here are some references. Before I go to details, some words about, does it work? Let's get this little here. Open. That's, yeah. Couple of papers before we go in details here. One of the first papers on Banach space regularization, let's see, the way from Hilbert space to Banach space, this is a little bit here, is the paper by Martin Burger and Stanley Osher in 2004. And they introduced an old tool, the Bregman distance, to that theory, and showed that with this Bregman distance is so many possible here, and I was one of the referees of this paper. It's a silver bullet for this anyway. And really, they had 4 or 5 very interesting examples. I was very enthusiastic about the chances. And really, this paper was, one has to cite this paper in any case. So, depending on this and also using this technique of Bregman distance, we did in 2007, we published this paper with Ottmar Scherzer, Christiane Böschel, and Barbara Kaltenbacher here. And our notation is still a little bit old-fashioned from today's point of view, a little bit old-fashioned, but it was the first. With my colleague Thorsten Hein, we wrote something about approximate source condition for nonlinear problems using these things here. And in the same year, the book by Ottmar Scherzer and his colleagues appeared variational methods in imaging, which has a very nice chapter on Banach space regularization. Ottmar is always unhappy that nobody cites this book, but this depends on the title, I think. They do not know that there are so fine things about Banach space regularization is in this book here. A very interesting paper in this scenario is Markus Grasmeyer. He is now in Norway. Generalized fragment distances, he makes nice things, and also with non-convex regularization. In my talk, non-convex regularization does not occur, but he does also other interesting things. Together with Masahiro Yamamoto from the University of Tokyo, when I was in Tokyo in 2010, we discussed a little bit the things from other points of view. For example, with respect to effects of conditional stability. It's for the PDE fans, well-known things, conditional stability. I was extremely uninformed about this, and yeah, we could find some cross connections in that way. On Thursday, I will discuss conditional stability a little bit more. Radu Botz, he was, I think, 20 years in Chemnitz, did his habilitation in Chemnitz. Then he went to Heinz Engel, Ottmar Scherzer, to the University of Vienna, and he comes from convex optimization. I could put him a little bit to inverse problems, and he's a very strong person, and so it was a nice paper. I will mention it in. And so at the end of this little list, this book with Thomas Schuster and colleagues, where we tried to collect all those things. From my point of view, I have 2 chapters there, and yeah, I formulated the things which I think that Banach space regularization, from my point of view, is necessary to do there. Thank you for this patience concerning these things. I must just get das jetzt Ctrl L. Again, now 2 stars. 2 stars. The general theory, also in this book with Thomas Schuster, clearly formulated, is we have even-dimensional Banach spaces, really. Rn is also a nice Banach space, but here we should think at the moment about even-dimensional. We have dual spaces, X star, Y star, and we have a dual bearing, and we have such norms here. If I have Banach spaces here, I will use subscripts. Seems so. Thank you. All is clear. And I think, for me, and also for other people, I think also, Heinz Engel, when he wrote together with his colleagues his book in 1986 or so, then he also assumed always the forward operator should be continuous. But we do not need it. It is enough that the forward operator is continuous with respect to some weaker topologies. I call it here tau x, tau y, these weaker topologies. And the forward operator, okay, this form with some domain, and this is my 2-star version, only a recall from the last thing. Tikhonov type regularization is, for this talk today, completely under consideration, nothing but this. Next talk on Thursday, also Lavrentiev regularization a little bit. Tikhonov regularization in the general form assumed this way. If I go to Hilbert space with P equals 2, and I will keep this factor here. I will not keep this factor here. Very important that the domain of f and the domain of this penalty functional must be characterized so that this is not an empty set. Otherwise, it does not work. And the exponent is between 1 and infinity. 1 is a strange situation. Greater than 1, most things give. But if you have 1, if you have p equals 1, then you must have some additional characterizations. And I will have it in. I assume that we have a regularization parameter which is positive, and that there exists such a regularized solution, which is a minimizer here. Of course,
if p is very close to 1, what is the difference that you get from the p equals 1 case?
The difference is, I think, I cannot estimate it from the numerical point of view. I cannot say it, but there is the I call it the problem of having trivial solutions, because solutions which are x alpha delta for p equals n are minimizers of this with delta equals 1. So this is an effect which is complicated, and you have to handle this. So we have this point. Let's discuss it there. Otherwise, I cannot explain it in a good way here. Some characterizations which are here: Banach spaces, a convex subset as domain, and one word, because this is here in the audience all know it, but not all people in mathematics know it. If you make a model, for example, that you say we have a function to recover, and this function is non-negative, and you work with LP spaces, Banach spaces LP, and you say x is greater than 0 almost everywhere or so, no? Then you have a domain which is convex, but has not necessarily interior points. So, but here you only need the convexity, not the interior point. This is important for some points here. I only consider R as convex, and it should be weakly lower semi-continuous. This is only for the optimization guys. In order to work there, the domain is non-empty, and very important, or for me the most important point, this R, this penalty, must be stabilizing. I say stabilizing, which means nothing but the level sets of all elements from the domain where this R is smaller than one constant are with respect to this weak topology, weakly sequentially pre-compact, in the sense that every sequence xk from this has a subsequence which is in the weak topology convergent in x to some element. This is the stability, and this is the basis for regularization success here in this way. Stabilizing functionals and coercivity, closely, sometimes it is called only, the R is coercive. Case A, reflexive Banach space, and we choose as tau the standard weak convergence, which is well defined there. And so I always use this symbol. Again. So I will take this.
Let's remove this one, please. Sorry for that.
Sorry. Yeah. Please tell me if I put it too deep here. You see, in these characterizations, you have no requirements that you have strong convergence in any sense for the forward operator, strong continuity. It does not, this is not needed here. For reflexive Banach spaces, you have standard weak convergence as this tau convergence here, and you know the supremum of all elements in this way, smaller than infinity for all C, is stabilizing the closed unit ball in X is weakly sequentially pre-compact. So in principle, you can use such norms for reflexive Banach spaces together with a simple weak topology. For non-reflexive Banach spaces, what is the idea? For example, let's say we need for this X a pre-dual separable Banach space. For example, my example here will in this slides will be L1, small L1, and you have C0, the space of 0 sequences with a supremum norm as a pre-dual space there. So you can use it, and this is this set with is here XL1, small L1, and here C0, and it works, and you can use the weak star convergence here. And the same thing, if this exists for all C, then are stabilizing, since the closed unit ball in X is weak star sequentially pre-compact. This is the well-known sequential Banach a la Oclu theorem, which works here. So, so one can, for example, use these two ways as a standard R. An element we call R minimizing solution to our equation if under all solution this R is minimized. This is well known. R minimizing solution always exists under our assumption, and of course attainability, the Y is really in the range of this operator for this given, and yeah, it is necessary that there is a solution in XD. It means also in such element that the R of X are finite here. Results on existence, stability, and convergence, the first three things for regularization theory, can be found, for example, in our paper of 2007 or in the PhD thesis in Innsbruck of Christiane Böschel. And the interesting thing is that, yeah, I spoke with Ottmar Scherzer about this. So I'm rather sure there is chapter 3 in this paper. I'm rather sure that the complete chapter 3 is well known in the Russian literature of the 1980s. But nobody has read it, nobody understood it, and we will publish this paper and we will have a look. Is there a referee who knows that and will explain us, aha, in this paper of 1985 from this guy, nobody was there. We have published it. So maybe we have reinvented this in that way here. Existence needs regularized solutions exist, not necessarily unique, but they exist. Stability notes if your data, the data are noisy, but if this noise gets some additional noise and this noise goes to 0, let's say y delta is approximated by y delta n, and delta n goes to delta, and then the solutions must converge in any sense. What does it mean, convergence here? We are enough happy if this is convergence in the weak topology tau x. So we have it in that way, and not more is necessary. What happens if you have weak topology and you have convergence in this weak topology, and you would like to have norm convergence? Then you need additional the property that the R must also converge. For example, if R is a norm, then the norms must converge. And so this is the well-known, in the simplest way, the well-known Radon-Ries property or Cadets-Clay property. Also, same thing. Different people have different names for the same things here. So in principle, with this Cadets-Clay property, you also have not only this weak, but also strong norm convergence here in this way. And convergence denotes that if delta goes to 0, then the regularized solutions converge to the exact solution. So convergence again in tau x, in the weak topology which we have here. So now the problem is what happens in nonlinearity. You have maybe an infinite set of solutions. So you make such a delta as a sequence, delta n goes to 0. Then you have a sequence of regularized solutions, and one can only say the subsequences must have the property that every subsequence which is convergence converges to any of the solutions which occur here, in this case to R minimizing solutions. So this is the general theory. In our book with Thomas, we have formulated this in one chapter. If anybody wants to read it in detail, it's very technical and it does not use to discuss it here. Now the more interesting point is, we know everybody wants to have convergence rates. And convergence rates can be in the sense of an error measure and wie lange habe ich? Okay. An error measure, and I call this error measure here E. E is a very general form of an error measure. It must be non-negative, and it should say something about the distance of some element to the exact solution. So what can be used for this? The simplest form is the error measure always used in Hilbert space regularization, the norm or some power of the norm. In reflexive Banach spaces, we often exploit this Bregman distance already mentioned. This Bregman distance is a very nice form of an error measure, and it is characterized, I have written it here. It works, of course, only for convex penalty functionals. The difference of this R of x, this R of x dagger, and this duality product here in this way. And you see this element must be defined. This is nothing but an element from the subdifferential, subgradient in this way, which exists, and we know if X is the Banach space, the subgradient comes from the dual of this. So you have here this dual element, this original element, and so this dual bearing works, and you can define the Bregman distance in that way. Really, Bregman distance is not a norm. Bregman distance is something other than the norm, but many people can interpret it, can work with this, and so it became rather popular here in this way. It's important to say this domain is called Bregman domain, is the set of all x from dr, from the definition, such that this subgradient set subdifferential is not empty here. And in general, this is some assumption one should always say. In the last year, there appeared a paper by Stefan Kindermann from Linz, and he did a nice thing. He said, okay, but one can switch the elements here. One can use, instead of x dagger, you can change the elements, and I said, okay, what does it mean, change the elements? Then you have subgradients of the regularized solutions. It's difficult to interpret, but he could show that there can be found nice results in that way. And I will say something later on this point here. Assumption 2, only some technical things I need. I need, if I have Bregman distance, then the domain should be so that we have this element in the Bregman domain. And with respect to nonlinearity, I do not use Fréchet differentiability in general. For me, it's enough in the solution that I have a linear operator, which I call f prime, like Gateau derivative, with the properties that this Limes characterization is true, and you see this is the same as you have for Gateau differentiation, but here this is a linear bounded operator and has properties like a Gateau derivative, but the good thing here is you only need it for directions which are in the domain, so it's less than Gateau. It's a directional derivative here. It's enough for the theory in this way. So for the evening, very yes, let's say abstract things here, but so examples, maybe a little bit for getting more insight. Back to Hilbert spaces very briefly here. You have Hilbert spaces, and you take this kind of penalty, well known from the paper of Engel, Kunisch, Neubauer, 1989. This was seminal paper in this theory, nonlinear Tikhonov regularization with convergence rates, such square root of delta rates could be shown. And he would say the three authors use this. Also in the book of Engel, Hanke, Neubauer, it was reproduced and it was written a little bit more smart there. And you see all is fine here. This is a singleton. This subgradient is nothing but such a Gateau derivative which exists here and has this special nice form. And the Bregman distance is nothing but the norm square. So all the things work. You have a compatibility here with the old theory and with the general theory of Banach spaces. Second form of Hilbert space situation, you take instead of the norm here S applied to the norm, and S is an unbounded self-adjoint operator. You can do the same things. The subgradient attains the form that the S square appears here, and this Bregman distance is nothing but this norm difference, but now with this differential operator here. The domain is a domain of S squared here. So in principle, differentiation or penalties of differential form occur in this theory. But now, sorry? Good question, but no answer from my side. I do not see it at the moment. Maybe, but do not see it. Sorry. Do you know the paper? I will show you. Maybe you have it. Interesting thing. Interesting thing. In general Banach spaces, many people, particularly a group of Thomas, was interesting in situation that the penalty has this form, norm, is only a factor, not important, norm to the power q. And they thought about LQ spaces. So this attains the form of the integral, so it's a rather simple form. And they use Tikhonov regularization. The function to be minimized, a functional to be minimized, has this misfit term with some power p, for example, also in LP spaces, and this with q, for example, the x, the y in LP spaces, the x in LQ spaces, both greater than or equal to 1. 1 is always a problem in some points. And you have the situation very clear. And now this so-called duality mappings comes into play. And this duality mapping from x to x star occurs also in this Bregman distance. You see this norm difference, and here you see as the operator this duality mapping occurs here. These are the examples for the really hard guys of Banach space regularization. They like this form, and the half of the book goes about this thing and all around this. This is a part one really understands very well. Now something which is for me more familiar, the question, okay, what I want is such a convergence rate. Convergence rate, my error measure should be big O of phi of delta, and now again my index function with some concave index function in this way. Index function, such a function, continuous, strictly increasing with this limit from the right hand to the 0, with this such rate function occur here. And such rate results are the central idea, the central goal of this characterization. And it is clear many things must fit in order to get it. So I want to characterize these many things. One point is you need some choice of the regularization parameter. You can do it as a priori parameter choice. You can do it as a posteriori parameter choice. Of course, you can do it as a heuristic parameter choice, but you have no theoretical result. From practical point of view, I often use this. I often use L-curves. I often use quasi-optimality characteristics. But anyway, there's some problem. You need also some paper from Kindermann. You need some characterization of the noise. The noise must have a specific character in order to get something. I will not do something in this direction. The appropriate interplay of all model components is necessary, is important, and I have I have listed for you what has to fit. The smoothness of the solution, for example, in form of such source conditions or distance functions, the non-linearity structure of the forward operator, the properties of the penalty, and the character of the error measures. And if all these four fit, then you get convergence rates. So I did not speak up to now about the non-linearity structure. The non-linearity structure is an interesting thing because if you have a nonlinear problem, you must characterize the non-linearity for around the solution or in general. And so in 1994, it's a couple of years ago, we discussed with Ottmar Scherzer, can one bring this in a, one always tries to find a general solution. Mostly it does not work. We tried to find a definition for this, and we called it degree of nonlinearity at some points. Degree of nonlinearity at such a point x dagger. And we said it always works with Taylor remainders. And so one can consider the Taylor remainder in the following way. You have f of x, you have f at the solution point, you have this f prime in the simple way, one-sided directional derivative, x minus x dagger, and this is the remainder. And our ideas in this old paper was, we have a constant, and after this constant we have three factors. The first factor is fx minus fx dagger to some power, let's say c1. The second is f prime of x applied to x minus x dagger to some factor c2. And the third is x minus x dagger with some exponent c3. And we say degree of nonlinearity and call it, this is degree c1, c2, c3. So it was a little bit too simple form, but some aspects of this really work. You all know the situation that c1 is 0, c2 is 0, and c3 is 2. This is a well-known thing. I will have it in different points here. This is the simplest situation. This is the simplest and mostly occurring condition which can be used for this. It really exists for other convolution problems. It's the only which exists there. But our discussion started with the point, what is the specific, this you can do for inverse problem, for well-posed problems. The specific point is to get this term with some C1 greater than 0 on the right-hand side. If you have it, then you are in a very well-known world and a very fine world. If you have, for example, C1 is 1, then you have some kind of tangential cone condition. And this tangential cone condition is so helpful for things. It's enough to have it for x in a ball here around this x dagger, or in a closed ball here around. This is enough. And so the question C1 greater than 0 is the mostly important point. If you have it, then you have a better world. If you haven't it, then the situation is, yeah, it's simple, you can work, but you need, if you have a look at convergence rate results, if you think about the seminal paper by Engel, Kundisch, Neubauer, 89, then they have it. This condition, C1 is 0, C2 is 0, C3 is 2. And they have a source condition in the sense of x dagger is A star. A is here F prime of x dagger star. And now, this is the collateral damage of this problem, you have a smallness condition. Some L times W must smaller than 1. L is here some element, which I will have it in this way. So if you have this C1 greater than 0, no smallness conditions occur. This is the nice world of the, but this is the world which rarely occurs, and it is very difficult to show tangential cone conditions in the practical situation. So, but if you have it, then it's fine. So this specific thing that these F differences remain very small, even if this left-hand side is not so small. This is the most important point, which for which we have to distinguish the well-posed and the ill-posed situations in the nonlinearity. So aspects of this will occur in the slides at some points later. We call conditions which help link conditions here, and I already told about source conditions, about such degree of nonlinearity, and the question before we start with hard Banach space, let's learn something from Hilbert space situation. Learn a little bit about, and so I go back to the classical theory, Engel, Kundisch, Neubauer theory, I call it always. This is the classical form. I skipped here the half as factor, it's not so important, it's only a form of writing. All is well known there, and instead of R minimizing, you have here the X bar minimum norm solutions. You search for the solutions which have the property that the solution is the nearest to some reference element. If you have in linear problems, you take 0 because you can shift, but in nonlinearity, it may happen that you need such element because it occurs here. Moreover, under these conditions, the regularized solution always exists, independent of the noisy elements, and all is fine. You can work with this. You have all the properties I assumed here, and yeah, for the nonlinearity, of course, you need some assumptions. Engel used Fauché derivatives here even, but this is too much to have it. Now, this important part, which comes back to this degree here, Engel assumed nothing but such a degree. This is C1 is 0, C2 is 0, C3 is 2, and you have such a form. This is nothing but a Lipschitz property of the Gateau derivative of the directional derivative you have here. And yeah, with this, you can get this result. This is the seminal result. You see it here. You have this benchmark source condition in that form. If we take x dagger minus x bar is in the range of f prime x dagger of the adjoint of this, and you need, because you have only this third, you need such a smallness condition, you get it. For the regularization parameter choice, this is a well-known and assumed to be a standard characterization. Alpha must go to 0, but slow enough. in order slow enough, denotes that this must also go to 0. If it's too fast, then and all people think this is the regularization has these properties. But on Thursday I will show we have two other situations. This goes not to 0, but remains between two constants, and this goes to infinity in case of over-regularization, if the penalty has the property that the regularized solution, that the exact solution has always r of x dagger is infinity, then this quotient must go to infinity. So this is an interesting, nice effect. I didn't know it a year before, but we have seen it. So for this simple model we have now, it is right, and under this condition you have convergence in the sense of subsequences and in the weak convergence. And consequently, one interesting point, if multiple x bar minimum norm solutions exist, then only one of them can satisfy the benchmark source condition together with the smallness condition. If you have this, you cannot have two different such elements which solve this condition. So if you have a situation that from one point two different solutions have the same distance, you can never have such convergence rates, because it's a conflict with this here. If the benchmark source conditions or the smallness conditions have to be satisfied, then you can characterize the things and you get convergence rates under low order source condition. For example, Hölder source conditions in that way. You see nu is smaller than a half. That means this is the A star A with exponent characterization which we have here, the power type of such source conditions. And if alpha has this a priori choice, then we get convergence rate in this way. And you see if nu is smaller than 1, then you see 2 plus 1, and you have here 2 over 3. And this is well known, this is some kind of saturation. If nu is a half, then you get such saturation situation here. The logarithmic in the same way, then if you have such a logarithmic source condition, you get such a logarithmic rates in this way. Now something again about aspects of this degree of nonlinearity, the tangential cone condition. In my writing, tangential cone condition is such a condition that you have here C1 is 1 and the other are 0. So, and you see the C is some element. For the guys from iterative regularization, they in general need C smaller than 1 in order to work with. Here, I say tangential cone condition, even if there is some thing. And this is a very important condition. And so the next idea is, if this is too strong to satisfy for a practical problem, then maybe you can have a concave function. For example, a power phi of t is t or square root of t. Then you can reduce the strength of the tangential cone condition in that way. I call it phi as an index function of condition of tangential cone type, where phi is such a concave index function. And yeah, one can work with this. If you have this instead of the tangential cone condition, all the good things which I discussed here do occur. All the good things are satisfied. You do not need smallness conditions, but it is not so simple for practical problems to find such phi functions such that it works. Yeah, convergence rates under benchmark source condition and phi situation can be shown, and you get error estimate with E as a simple norm difference and big O of square root of phi of delta. That means if you have the benchmark source condition in Hilbert space situation, and instead of tangential cone condition you have this simpler, then you find this here in the rate. The rate gets worse.
Bernd, can I ask you a question, please? Suppose that in the previous slide you introduced this index function now. Is there a way of controlling the Landweber iteration and ensuring it using phi instead of the...
No. I think no. Landweber iteration needs not only such c, it needs a small c.
Yes, right, but perhaps you can put conditions on phi so that
I do not know a result depending for iterative regularization with this condition. This is only for variational regularization, which I know, but maybe it exists. But sorry, I cannot make an affirmative assertion in this direction. So this is rather nice. So to have it, and now I come back to my distance function. I like it. The distance function, they occur in the same way here. If this benchmark source condition, I go back. This is the benchmark source condition. Yeah, the difference of solution and reference element is in the range of f prime star. And if this is too much for the smoothness of X dagger, if X dagger is not strong enough, not smooth enough, then you can work in this technique of distance function. You can define here the distance function. In that way, you see the same as I explained here, now here as a difference with a reference element in the nonlinear way. And this distance function, if here technical assumption injectivity of f prime in this way, this goes to 0 as a convex function, and you know it exists. Often you can estimate it, and you can evaluate the total error so that the error norm is big O of, and now interesting thing, the distance function as a function of delta, noise level, and here this function contains this phi, and it contains such a construction. This distance function of r squared divided by r. This is rather technical thing. You can, if you know the d function, you can compute it, and you see, and always you will find this rate will be worse than the square root rate in the original case. Always worse, it's clear. You have not the smoothness of the benchmark. You have not the rate at all in this way. Yeah, Barbara Kaltenbacher is a big fan of other forms of such non-linearity condition, and she likes left side rotation and right side rotation in that way. And all who characterized iterative regularization will know these things because they are very interesting for Landweber, for such things. There must be such a rotating operator with the property that the rotating operator minus the identity can be characterized by the right-hand side with such power of the x differences. and in the otherwise same thing, but the rotation is on the right-hand side. So this is left hand and right hand occur in papers by Barbara. She summarized the chances of this kind. So it was interesting for me because I did not work with it. For the left-hand side version, you see it. This is the left-hand side version. The R is on the left-hand side. You can make simple computations. You take this remainder. You make here a mean value theorem. Here a little bit more assumption about the f prime is unnecessary. Smoothness assumptions here in the neighborhood. Yes, you estimate this by this R here. You can characterize this by some CR in this way because you have this left-hand characterization, and you find this way, and you see then this this remainder can be characterized by a constant, and if you see here the right hand, and you see two of this, but C2 and the C3 occur here. The C2 is here 1. The C3 is this kappa which occurs in this way. So in principle, you have a nice characterization. If this x is near enough, you have here constants which are smaller than 1, and you can work with this in a good way. For example, you have this characterization, and you can show in that way that the characterization of the remainder has a constant multiplied by this f prime, and so we have here C2 and S1 in this way. And on the other hand, by using the triangle inequality, we even derived the tangential cone condition in case that the R is sufficiently small. That means this is a small value, so this is a small constant, which is also a consequence of this L. So in that way, this is the left version is very near to tangential cone condition here in this way. So some summary of this point. There is a complete deficit in low-order convergence rates if two things occur. The first, the benchmark source condition fails, which means that the X-dagger is too non-smooth, and L and R, and there is no convex index function in that way, such that phi holds. Both fail. This phi does not, which means that the structure of the nonlinearity is too poor. If the smoothness is too bad and the nonlinearity structure too poor, we have no convergence rates results, nothing. And yeah, this is not nice, but this is a deficit which occurs at the moment. And it's in Hilbert space. It's not in Banach space. It's in Hilbert space. There is some lack in this point.
Rotation and range invariance condition is the same.
Yeah, there exist different versions, but this is much stronger in this way. I think therefore, at the end, some words about autoconvolution equation in the real space again. You remember autoconvolution? I can consider this here as a autoconvolution between real Hilbert spaces L2 1, 0 of the unit interval, defined in that way, and yeah, such simple characterization, simple quadratic thing, and the question is it possible to get simple rate results in this way? So the first question, is this really a ill-posed problem? And I recall the definition of local ill-posedness and local well-posedness. Here still written in a little bit otherwise. Otherwise, if not well-posed situations, we call it locally ill-posed, which means that for arbitrary small radii, there exist sequences such that this f difference for n to infinity goes to 0, but the elements do not meet in this sense. But for arbitrary small radii, that means you have only a local characterization. what outside of such a radius happens, nobody's interested here for this. And so that you have really one example. For this autoconvolution problem, you can simply characterize this. You take this xn in that way. You have this x dagger in the standard form until some remaining part on the right end between 1 and 1 minus 1 over n. And you add in this interval, in this small interval, r times square root of n, and you simply see in L2, yeah, the difference is r. But you can, for autoconvolution, you can characterize the f difference, and you can estimate it in that way. And you see this is 2r divided by square root of n multiplied by this fixed value, and you see this goes to 0 as n goes to 0. This means this problem is locally ill-posed everywhere at every point. So you can do what you want. You have to regularize in this way. The ill-posedness occurs. Also, the nonlinear autoconvolution is not compact. You can show that the autoconvolution operator in this form is not compact. It can be seen in a rather simple way, but the Frechet derivative exists at all points and is such a simple linear convolution operator and is compact. So we all know if you have a compact nonlinear operator, then the derivatives are also compact, but not reverse. Here we have a nonlinear operator which is not compact and the derivative is compact. So this is a rare situation. I do not have many examples of this way. And this makes the problem of the autoconvolution also a little bit complicated, I think. It's one of the reasons. Based on Titchmarsh's theorem, one can show that the operator f prime is injective if the supremum of taus with the properties in the interval from 0 to tau bar, this is almost everywhere 0. And if this supremum is 0, then you have injectivity. And under this condition, you can show you have a solution x dagger and you have a solution minus x dagger, because if you see it for the f's, here I go back, if you see it for the f's, then yeah, if x and minus x are multiplied, and if you have a solution, then minus x is also a solution here. So you have really just exactly two solutions under this injectivity characterization. And now the nice point, one can show that f is weakly sequentially closed, weakly continuous, and this is the only one you have. This remainder of the Taylor part is just the autoconvolution of x minus x dagger with itself norm squared. So, and you have C2, C3 equals 2, and you have this characterization, this property of Engel, Kunisch, and Neubauer in that way. And with such condition, Lipschitz condition, with k equals 1. So, and one can show such a proposition for the autoconvolution operator under consideration here. In any element, there is no index function eta in such a way that this f difference can be estimated by such an index function of the f primes. So seems to be rather technical, but it has many consequences. I have here in the slides the proof. It's not so interesting for this evening, I think. So a corollary of this is the following. For the autoconvolution operator, such a prime condition and consequently a nonlinearity condition L cannot hold. L is lost for these things because of this inequality we just had. Moreover, also the tangential cone condition cannot hold with a constant smaller than 1. So we have shown there is no tangential cone condition with a constant smaller than 1. Proof is also here. I think I skip it here. And now, interesting thing, and question to all in the audience in the evening. Please show that the tangential cone condition can never hold also for c greater or equal 1. And yeah, that's, which means we conjecture this in this way. This conjecture, if this conjecture here is true, then the outer convolution operator cannot have this tangential cone condition. In order to understand it a little bit simpler, let's take x dagger is identical one function. From 0 to 1, always 1. Then you can write it so. This is the primitive in capital H, and small h is the difference of the function, and tangential cone condition denotes this outer convolution of this small h, smaller than r in the norm, must be smaller than this primitive 2 times plus this for all h in such a radius. So to show that this never can occur, it would be enough to show that there is always a sequence hn such that this limit goes to 0. We have done much work there, did not succeed to get it. Jens Fleming made numerical experiments up to 16 digits, and he showed this it cannot occur. It cannot happen. The DCC is not possibly, but we have no analytic proof. My colleague Albrecht Böttcher told me, this is the modern mathematics. You have numerical experiments, but you cannot show such an important thing. So yeah, he is right, but we could not. But we believe that it does not hold. But if anybody, even for this situation, specific situation, this would be very, very nice. Please tell me, please write me if you have a result in this way for this. So I think I'm over at the end, and I will continue on Thursday with some remaining part here. Thank you for your attention so long.
Okay, are there any questions or remarks? Please, Hamuli.
So the smoothness was a central concept in your approach. Does it always have to mean smoothness? I mean, in a function space for the functions globally defined in a domain, or could it be piecewise smoothness also? Local smoothness. Right.
From point to point, the non-linearity situation
yes.
can change from point to point.
Right.
Yeah. If you, for example, if you take in the 1990s, we thought that it's enough to characterize the derivative.
Yes.
You take this outer convolution, take the derivative. You see if you have this function at this point and say, okay, this is a compact operator, the convolution of linear convolution operator, and you take the decay of the singular values, characterize it. You have very different. You have a very slow decay, a very fast decay. In every surrounding, you have all conditions there. So from point to point, you can completely get different things. So it's a local thing, and only for a couple of problems. For example, PDE problems are helpful. You have a continuity there. You have a robustness there.
Mm-hmm.
But outer convolution is completely non-robust. It's a local thing. If I say smoothness, then always for that solution, not
Right. Okay.
sorry. This
Yeah.
is not nice, but
Okay. Thank you.
Okay, any other question? If this is not the case, let's thank the speaker again. Thank you, Professor Hofmann.